plane elasticity. Oh, I guess just backing up to this problem, right? So the homework problem is very similar to this. It's just instead of elements, it has triangles. So you have to, and you already know what the triangle element stiffness matrices are, right? So it should be pretty straightforward. All right, so plane elasticity. This is like two-dimensional elasticity. And while we didn't, I briefly mentioned it when we talked about when we did the elasticity theory, like in the first part of the class. I briefly mentioned that there's like two conditions in which we can reduce the 3D problem to a 2D problem. One is called plane stress. So plane stress problems are typically when you have a very thin and long and slender but thin plate, right? And that's because you assume that the stress through the thickness is zero. And the other one is plane strain. So plane strain is when you have a very thick through the thickness specimen. So you're solving something in the plane, but you have a very thick specimen, such as you assume that, because remember, strain is like change in length over length. Well, if the change in length is small and the length is big, then effectively that strain is zero, right? So plane strain would be that problem. So we're going to, and I didn't have time to introduce them then, but there are different elastic constants you use based on the two conditions. But for now, we can sort of move forward without knowing exactly the form of them. We'll just, in the elastic contrast matrix, we'll just have C's and we'll work with those. Okay. All right, so our conservation of momentum in 2 dimensions then that's one equation. That's 2 equations, right? It's just F equals MA. And we're only working in 2 dimensions here. So there's no third equation, but if you were in 3 dimensions, there would be a third equation, and you'd have an additional partial of the stress with respect to x3 in all the equations. But what we can do here is we'll introduce what we'll call a stress vector. So we'll call it stress bar. Since it's only got 3 components, and we'll write sigma 1, 1, sigma 2, 2, sigma 1, 2. And then we're going to introduce this operator matrix that is partial x1, 0, partial x2, 0, partial x2, partial x1. So then with those 2 things, we can write the equations above more compactly in matrix form. So we have D transpose that operates on the stress vector, right? So you should be able to see, right, if I take the stress vector and multiply sigma 1, 1, sigma 1, 2, right? And then sigma 2, 2, 2, sigma 1, 2, 1, right? Oh, it looks like I have. Yeah, no, that's right. We're good. Yeah. So that stress vector multiplied by this operator then gives you those terms, right? Plus rho B vector equals rho U vector double dot, right? Mass times acceleration, where the B vector is B1, B2, and the u vector is equal to u1, u2. So that's that same we can use that same partial derivative operator matrix D. If we operate on U, then we can get the strains, right? Where the strain vector is like that, and you get the, if you don't remember why it's 2 times epsilon 1, 2, go back and look at the notes, right? When we're talking about linearized strain theory. So then we can write a constitutive model that relates stress to strain. So stress vector, well, let me just write it out first. So stress 1, 1, 2, 2, 1, 2 is equal to C11, C12, 0, C12, C22, 0, 0, 0, C. We'll just call this C33. No, I don't want to call it C33. What is it? It's actually the 6,6 component from the larger, the 81 component matrix. So I guess I'll leave it as that. 2 epsilon 1, 2. But yeah, basically you have to look up, theCij's are elastic constants or elastic properties that are different depending on plane stress or plane strain. Again, those would just be functions of like the Young's modulus Poisson ratio, those things. We can look those up. But for now, we're just going to leave it in this matrix form so that we can write this stress is equal to C times epsilon. So again, writing our equation, D transpose, and I'm just going to rewrite it to move this D transpose to the left-hand side of the equal sign so that we have minus rho B plus rho U double dot. And the reason is I'm going to modify what's on the left and I'm going to leave this alone. So this is equal to then, right, if we plug in this equation, stress equals to C times strain for the stress right there, right? Then we have D transpose C epsilon. And then if we plug in this relationship, epsilon equals to D times U, right there, then we have D transpose times C times D times U. And then that's equal to the right-hand side. So we also have the boundary conditions. T1 equal to or in vector notation, it's just the Cauchy stress equation, but using our new definition of stress, right? The stress vector, the 3-component stress vector. And then we could have essential boundary conditions as well. Right? So with that, it looks like we have about 6 minutes, which is going to be about just enough to write this down. If the bell does ring, let me just finish this because this will bring us to a nice stopping place. All right, so then we're going to develop the weak form. And I'm just going to write down. So we're going to integrate over the volume of the element. It'll be sigma ij delta epsilon ij plus rho ui delta ui dve minus integral over the volume of the element bi del ui dv integral over the surface of the element but in 2D the volume of the element, what we'll say is the thickness or depth, like into the pool, into the blank, right? We're going to solve 2D problems in the plane, so they'll have some thickness, right, times the area of the element, right? And then, so with that, and I'll write out some terms here. So now you have HE here multiplying or using our matrix notation, we have so that's the weak form.
Is that over 2e, the second part, the integration?
Where?
The last statement, second integral.
This?
Yeah. Is it over 2e?
No. No, it's an HE times del U transpose, because it's a vector, times this vector. That's a dot product. Times,
The omega c looks like 2e.
oh, that's omega E. It's the same domain of integration as the other integral. Yeah. Okay. So again, just give me 2 minutes here just to finish this. So now this is the weak form. So then we'll use the Glurkin approximation. So we're going to assume that U is N times U, Nj, Uj, and then del U is N, right? And we're just going to plug those in. Right? So we have U of H, which is a vector now, whereas before it was a scalar, right? U1 H, U2 of H, that's equal to Nj, U1J, Nj, U2J, or N. And what I'm going to write here is just D, like it's a vector of unknowns, right? So it's the U's, but they're the nodal unknowns, okay? And then the biggest difference here is that we have N1, 0, N2, 0, dot, 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 N, 0, 0, N1, 0, N2, dot, 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 0, N, right? Because we have X and Y, right? So the shape functions are functions of X and Y. And if we're going to write it in a matrix form, then we need to multiply this vector of unknowns, which is the same length as the number of shape functions, right? The number of nodes in the element. So that times that, that'll give us 2 values, right? So again, D is just the vector of unknowns. So it's like U1 for element 1, U2 for element 1, U1 for element 2, U2 for element 2, U1, dot, 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 U1 for element N, U2 for element N. And then del U is just N, okay? Also, we have that epsilon is equal to D times U of H, which is equal to D times N times D, right? And this thing we call B, the strain displacement matrix. Okay, finally, last equation. Plugging all that in, our finite element model is the integral over the domain of the element HE B transpose C B integrated over dx times the vector of unknowns D plus the integral HE rho N transpose N dx times D double dot minus the integral HE rho N T B dx minus the surface integral HE N transpose times T ds, right? So this is what we call the element stiffness matrix. This is called the mass matrix. This is F. This is Q. So then in matrix form we have K times D is equal to, K times D plus m times d double dot minus f minus q is equal to 0. Or in quasi-statics, we assume that that term is 0, and we have k d equals f, which equals to f plus q. Right? So in the end, it's just the same kind of linear system that we have to solve. If we want to solve the dynamic problem, then we have to do something about this. Okay, we have to discretize this in time in some way. Using basically, at this point we have ODEs, right? A matrix system of ODEs. So then we can use an ODE time integrator in time. Right? All right, so that's plane elasticity, right? The scalar problems we solved are similar to like diffusion problems, right? Now we have elasticity. So finally, next Tuesday, we'll be able to combine them to write down the matrix equations or the finite element model for the poroelastic system. Okay.